Avogadro's law. Avogadro stated that at a given temperature and pressure, the same number of gas molecules will occupy the same volume regardless of the type of gas. So what does that mean? That means if I had a balloon, I'm on a race, hold on a second here. If I had a balloon, and that balloon was full of oxygen gas, and those were flying around in there, and then I had another balloon, and it's at the same temperature, same pressure, if the number of helium gas molecules in that balloon is the same as the number of oxygen gas molecules, if the number of particles is the same, the volume will be the same. And the type of gas doesn't matter. When I first heard this, it seemed very strange to me, because when I think of pressure, I'm remembering that pressure is force per unit area. I'm thinking to myself, shouldn't the heavier oxygen gas molecules, keeping in mind that each oxygen gas molecule would have a mass of 32U in comparison to the mass of the helium gas molecules, which would be 4U, shouldn't the heavier oxygen gas molecules exert more pressure, deliver a bigger hit when they hit the side of the container, and as a result expand the balloon more and cause it to have a larger volume? But the trick with this has to do with the speed of the molecules and temperature. At a common temperature, bigger gas molecules move slower than small gas molecules. So the oxygen buzzing around here wouldn't be buzzing around as fast as the helium. These two factors compensate for each other. So as the mass goes up, the speed goes down, and so the overall force upon collision remains constant. Or if the mass goes down and the speed goes up, again, the force remains constant. So, because of this compensation with mass and speed, regardless of the type of particles, the actual force delivered in the collisions will be the same, and so they occupy the same amount of volume regardless of the type of gas. Knowing that the volume could predict a common number of gas molecules, Avogadro had a way to set an arbitrary number as the number that we're going to call the mole. There were two standards used: standard temperature and pressure. T equals 0 degrees or 273 Kelvin, and pressure is 101.3 kPa. 1 mole of gas will occupy 22.4 liters. So if we imagine our balloon was 22.4 liters big, that set the mass of carbon to 12 grams, or the mass of hydrogen to 1 gram of that gas occupying that space. And so they defined the mole. And that's how they actually picked the mole in the first place. They said anything that has this temperature and this pressure and is gas, 1 mole of it occupies 22.4 liters. So then they could get a mole of hydrogen, they could get a mole of oxygen, they could get a mole of helium, and they could compare the actual masses of those elements when they're at that fixed volume. Now, working in a lab at 0 degrees Celsius doesn't sound great to me, so somebody came along and invented standard ambient temperature and pressure. Here we're going to have our lab set at 25 degrees Celsius, much more comfortable, at 298 degrees Kelvin. Pressure is 100 kilopascals, and that raise in temperature is going to lead to a slightly larger standard volume, which we call 24.8 liters. So we can say a mole of gas is going to be, or the number of moles of something we have is going to be equal to their volume divided by one of these standards, either 22.4 or 24.8, depending on which set of conditions we're operating at. And that's how the mole got defined.